the last class we have seen that when a file is to be opened, then if the system knows that what is the inode number of the file, then firstly what the kernel has to do is, whenever such an open system call comes, it has to find out whether the corresponding inode is present in the in-core memory or not, in the main memory or not. So that will be done using an algorithm which is, we have said this is an IGET algorithm, which performs the task of searching for an inode in the main memory. So if it finds an inode in the main memory, in that case that inode will be returned to the requesting process. In case the inode is not present in the main memory, then what the system has to do is it has to find out a new inode, a free inode, in case a free inode is available on the free inode list. If the free inode is not available, then the system will return an error message that if no inode on free list, then the kernel will return an error message to the process who has requested for it. But in case there is one or more free inodes on the free inode list, in that case one of those free inodes following the same LRU principle, least recently used principle, will be taken out of the free inode list. This inode will be returned to the requesting process, which will be used for copying the disk inode into main memory. And after that, the process will have access to inode. That means that once the process has access to the inode, it has access to each and every disk block which contains the data of the requested file. Similarly, when a process closes a file, the corresponding inode should be returned to the free inode list, provided there is no other process for which the inode is active. So for that, the algorithm we have discussed is IPUT algorithm. So IPUT algorithm, what does is it decrements the reference count by 1. So after decrementing reference count by 1, if the reference count becomes equal to 0, that indicates there is no other process for which this inode is active. So if reference count becomes 0, in that case the inode will be put on the free inode list, and before that, in case the inode is changed, the changed information has to be updated onto the disk. Okay. Now if the reference count is not equal to 0, that means that though this process has closed the file, but the file is open for some other process. Okay, that means the inode is still active for some other process, and in that case the inode cannot be put onto the free list. So the kernel will simply return after decrementing the reference count field. Okay. So both this IPUT algorithm and IGET algorithm, it assumes that the kernel knows that what is the inode number which is being looked for. Okay. But usually when you open a file, either for reading purpose or for updation purpose, what you give is the file name. Either the file name with respect to the current directory, or file name, complete path name of the file which is needed from the root directory. Okay. So we must have some mechanism by which this file name or the path name can be converted to the corresponding inode number. So before coming to that algorithm, let me say that what is a directory? And I think we have mentioned that directory is nothing but a special kind of file. Okay. So for every directory and every file in the system, on the file system, we have to have an inode. For a directory, we'll have an inode. Even for a file, we will have an inode. Okay. And the type field in the inode has got a type field. The type field in the inode will tell you that whether it is a directory or a file. Okay. Not only that, the type field also says whether the inode is free. That means the inode is not allocated. Free does, when I'm saying free, this does not mean that it is not being used by any process. The inode has not been allocated to any file or any directory. Okay, that is an unallocated inode. So the type field also specifies whether the inode is still unallocated. If it is unallocated, then it can be allocated to a newly created file or a newly created directory. Okay. So the type field will indicate that whether the inode is unallocated. If the type field contains a value 0, then that means the inode is unallocated. It will also indicate whether the inode is for a file or the inode is for a directory. So directory is also nothing but a special kind of file which contains a list of entries. That means list of other files or other subdirectories within this directory. Okay, and in fact this is the directory which gives the file system a tree-like structure. And there will be a particular directory in every file system which is called the root directory. Okay, and the root directory will also have a corresponding inode. And the inode of the root directory, when the system is booted, will be stored in a global variable which is accessible to every process. Okay. Now, when I say that directory is nothing but a special kind of file, so it also contains a number of data. And this data in the directory represents a list of inodes, and for every inode, what is the corresponding directory or what is the corresponding file. Okay. So it will be something like this. The content of a directory will be a list of inode and file name pairs. File name, or this can even be subdirectory. So the directory will contain a list of these pairs. Okay. There will be two special entries named as dot and dot dot. Whenever you have given any directory listing, you must have noticed that first two entries are dot and dot dot. The dot will have one inode. Let us say that some inode number say 83. Dot dot will have another inode number. Suppose this inode number is 50. Dot means it is the entry for the current directory. And when I say that this is inode number 83, for entry dot the inode number is 83, that means the current directory, the directory which is under consideration, that is having an inode number 83. And dot dot indicates the inode number of its parent directory. Okay. So you must have seen that whenever you want to go from any directory to its parent directory, you must have given cd dot dot. So following cd dot dot, you just go to the parent directory. So this dot dot indicates the entry corresponding to the parent directory, and this is the inode of the inode number of the parent directory. And there will be other such entries. For example, if this directory is say directory etc, okay, in that case there will be a number of entries. For example, password file. Okay, there can be a subdirectory say bin. There can be a file called say make file system, things like this. For each of them, there will be a corresponding inode. Suppose this will have an inode number say 61, this can have an inode number say 30, anything as it is allocated. This make file system, this can have an inode number say 99, and so on. Okay, so the content of a directory is just like this. Now, when I said bin is a subdirectory for which the corresponding inode number is 30. So in the type field of inode number 30, it will be indicated whether this is a directory or it's a file. Password, this is a file, corresponding inode number is 61. So in inode number 61, it will be indicated whether password is a file or a directory. Okay. So whenever we want to open a file using a open system call, though we use that as a function, but it is nothing but a system call. Okay. So sometimes we can give a file name as say just password if the current directory is etc. Okay, or we can also give the path name as /etc/password. Okay, so this indicates that the path name starts from the root. Okay, and this is the entire path name leading to the file password. Okay, Whereas in this case, if we are in the current directory password, then simply this will indicate that we are looking for password file within the current directory. So I can specify a file name either like this or like this. So whichever way I specify the file, I have to find out what is the inode number of the corresponding file or the corresponding directory which we are interested in. Okay. So there should be an algorithm which converts the path name or the file name to the corresponding inode number. So let us call this algorithm as, say, name I, which will convert the file name or the path name to the inode number. So input to this algorithm will be the path name and output will be an inode number. Okay. So the algorithm will be like this. First we have to check whether it starts from root or it is in the current directory. So if path name starts from root, then we say working inode is equal to root inode. Okay. Else as I said, the root inode is stored in a global variable, whereas the current directory inode is stored in the user area. Okay. And after that, the algorithm will look like this. While this is read next path name component from the input. So while there is more path name, we have to read the next path name component from the input. Then we have to check that this path name we have to look in the current directory or in the working directory. So we have to check before we search for this particular path name, we have to check whether this working directory is or working inode is the inode of a directory or not. If and only if it is the inode of a directory, then only we can search in the directory to match for this path name component. Okay. Not only that, it has to be a directory. At the same time, the process should have the search permission in that directory. Okay. So as we have said that for every directory or for every file, we have a number of permissions given by read, write and execute. Okay, read means you can read the content, write means you can write into the file or modify the file, and execute is you can execute the file. In case of a directory, you can search within the directory if you have execute permission on the directory. So execute permission on the directory and execute permission on the file is slightly different. Execute permission on a file means you can execute the file, whereas in case of a directory, the execute permission means you can search in the directory. Okay. So here we read the directory. After you read the directory, and you can read the directory provided you have the necessary permission. So once you read in the directory, and obviously for reading the directory you have to invoke the algorithm of block read. Okay. So once you read in the directory, then you have to search for this pathname component into this directory. So you have to see that if component matches so the full algorithm will be like this. First we check whether the path name starts from the root or it starts from the working directory. If the path name starts from the root, then we set working inode equal to root inode. Otherwise, we set working inode equal to current directory. Then, while there is more path name component, more components in the path name, then we have to read the next path name component from the input. Then we have to verify that this working inode under which we have to look for this component, that whether that working inode is of a directory or not. If it is not a directory, then under that there cannot be any other subdirectory or any other file name. So obviously there has to be an error. So if this is an working directory and if you have the access permission, the required access permission on the directory, then only I can read the directory. Once I read the directory, then I have to search for this pathname component which has been read from the input stream within this working directory. Okay, within this directory which has been read. So if this pathname component matches an entry in the directory, then I have to get the inode number of the matched component. Okay, so you see that in the directory structure we have said that for every file name or for every directory I have the corresponding inode number. So I have to record this inode number for which I get a match. Okay. Then this inode number has to be the working inode number. Okay. And for making this as working inode, the previous working inode has to be released. So we release the previous working inode and make this working inode as inode of the matched component in the directory. Okay. And if there is no match, that means the path name which has been given is wrong. There is no corresponding inode corresponding to the path name component that has been specified. So you return with no inode. Okay, and this while loop will continue. The while loop starts from here, and it continues up to this. Okay, at the end of the while loop, when there is no more path name component, okay, that means the string has terminated, then whatever is the working inode at that point, that is the inode of the required file or the required directory. Okay, so you can open this inode, and once you open the inode, then you can access the contents of the file. Okay. Now all these algorithms, all these methods that we have discussed till now, that assumes that an inode is already allocated to a file. Okay, because so far we can open a file for reading purpose. We can also open a file for modifying the content of the file. So it assumes, even this nemi, it assumes that an inode is already bound to a file which is requested, or it is already bound to a directory which is requested. But if I want to open a file for creation, I want to create a file. In that case, there is no inode already allocated to that file. So I have to get a new inode and allocate that new inode, which is not allocated to any file or any directory so far. And that new inode has to be allocated to the file or the directory which is newly created. Okay. So the operation which is involved is you have to search for such an unallocated inode from the inode list. Okay. That is the list of inodes which are there in the inode blocks. And here again the super block comes into picture. As we have said, that the super block contains a number of informations, including that what is the size of the file system, okay, that is how big is the file system, how many files or how many directories it can store. Then it also contains information about the number of free blocks in the data blocks of the file system, the number of free inodes. Okay, it also indicates that where that free inode is available, because whenever I allocate a free inode or unallocated inode to a newly created file or a newly created directory, in that case contents of that inode has to be modified. All the fields in that inode are to be set properly. Okay, so you have to know that where that inode is available. Similarly, if I want to have a free block, suppose I already have a file and I want to add more and more data to the file. So naturally, it may require more number of data blocks. So I have to know where that free data block is available, and or how many such data blocks are available. So all these informations are contained in the super block. Now, whenever I want a new inode, in that case, usually what I have to do is I have to search the inode list on the inode blocks. For every inode, I have to check the file type field, because as we said, that type field equal to 0 indicates that the inode has not been allocated to any file or any directory. So I have to search the inodes which have type field equal to 0. Okay, those are the inodes which are not allocated, and I can take one of them and allocate to a newly created file or a newly created directory. Okay, so to help in the searching process, to reduce the time of search, a list of free inodes is maintained in the superblock, which is called a superblock free inode list. A superblock free inode list. It does not mean that this free inode list will contain the numbers of all the inodes which are free, but it will contain a subset of that. So whenever a new inode is to be allocated, firstly the kernel will try to see whether there is any inode in the superblock free inode list. If there is an inode in the superblock free inode list, in that case one of those inodes will be allocated to the requesting process. But if the superblock free inode list is empty, then only from the disk other free inodes will be taken. Okay, so the superblock free inode list is maintained like this, because this is nothing but a list of integers, because every inode number is an integer. So it contains a number of entries where every entry will be filled up by an integer number. Now what will be the initial situation? Initially, if I assume that I have a number of inodes which are free on the file system, because some of the inodes will be allocated to the system files whenever you load the operating system. There will be other inodes which are not allocated to any of the system files, which can be used for user data or user directory. So initially, suppose I have a number of inodes free, and the inodes numbering forms the inode number 400 are free. Okay. So the superblock free inode list will contain a list of such numbers in such a way that out of this, the first inode number which is to be allocated, or if I say that this is the head of the list will usually contain the minimum numbered inode indication. So this is 400, this one will be 401, this one will be 402, so like this it will continue, and suppose here the inode number is 499. If I assume that the superblock free inode list contains a list of 100 inodes. Okay. So it will look like this, and all the entries in the superblock free inode list are currently full. Now whenever a process asks for a inode, then because there are a number of free inodes indicated in the superblock free inode list, this inode will be taken and given to the process for to be allocated to either the file or the directory. Okay. And after this is given, this particular entry will be empty. Next time another process wants to create a new file or a new directory, the next inode will be given to that particular process, and it will continue, and it will continue till end. Okay. So whenever a process puts a request for an inode, for a new inode, always this superblock free inode list will be checked first. If there is an inode in this superblock free inode list, then the inode will be given from this. Okay. Now out of this last inode or highest numbered inode is called a remembered inode. Simply because of the fact that suppose I have a situation that all these 100 inodes have been allocated. So at a particular time, when this 499 is allocated, then the superblock free inode list becomes empty. Next time another process puts a request for an inode. First it will check the superblock free inode list. It will find that there is no inode in the superblock free inode list. So it has to get an inode from the disk. Now this 499, the highest numbered inode, this gives an indication that where a new free inode will be available on the disk inodes. Okay. So whenever this becomes empty, what the kernel will do, it will read next 100 inodes and fill up this superblock free inode list. Okay. So assuming that all other inodes from 500 onwards, they are all free, they are unallocated. So 100 inodes from that 500 till 599, these inodes will fill up the superblock free inode list. And after filling up the superblock free inode list, this inode number 500 will be given to the requesting process. Okay. So because this one, the highest numbered inode, gives you an indication that where you will get unallocated inodes on the file system, so this is called a remembered inode. So whenever, while getting a new inode, the kernel finds that the superblock free inode list is empty, it will immediately recall what was the remembered inode. Okay. And searching for free inodes will start from the remembered inode location. Okay. Because you know that once you know that what is the inode number, I can always find out the block which contains that inode number. Because the starting block where from I will have the inodes, that is fixed in a file system. Also the size of every inode is fixed. Size of every disk inode is fixed. So given an inode number, I can always find out that what is the block number which contains that inode. So if I know that what is the remembered inode, I can always find out very easily that what is the block number which contains the next free inode. which is likely to contain the least free inode. That may not be always true because the inodes will be allocated and unallocated. So it may be quite haphazard, but once I know that remembered inode, it is quite likely that the free inodes will be available after that, right? Now, similar concept comes that when an inode becomes unallocated. Now, this is the situation when a file is created or a directory is created for the first time, when I need an unallocated inode to be allocated to the new file or the new directory. Similarly, when you delete a file or when you delete a directory, earlier some inode was allocated to it, now that inode has to be unallocated. Now, once you unallocate that inode, the inode may be anything. Maybe I unallocate an inode or free an inode, this being the situation, and suppose out of this, or let me take another example. Suppose my situation was something like this. So 599 is the remembered inode. Then I have 598, so 597, and like this. And maybe there are a number of empty entries. Suppose these are all empty entries indicating that these inodes which are there in the superblock free inode list have been allocated. Okay, and I have other entries which are filled up by the inodes, something like this. So these three are empty entries. So whenever an inode is freed or unallocated, then I have to check what is the status of the superblock free inode list. If there is any empty entry in the superblock free inode list, what I'll do is I'll put the freed inode or unallocated inode into one of these empty entries. Okay, because this is an inode which has become free unallocated, so it can be allocated to any other requesting process. So you just store in one of these empty entries. If the superblock free inode list is full, say I have a situation like this, and an inode becomes free, there is no room within this superblock free inode list for this inode to be allocated, to be put. Okay. So in such cases, what is checked is you check the inode number of the remembered inode. If you find that the new inode which is becoming free, the number of that is less than this remembered inode, you simply replace the remembered inode by this new inode which is becoming free, if the number is less. If the number is more, then I don't have to touch this superblock free inode list. I simply mark it to be unallocated by setting its type field equal to 0 onto the disk. Because the number of that inode being more than the remembered inode number, the next time search for unallocated inodes is done, you will be able to access that particular inode. Because the search will always start from the number 499. And suppose the inode which is becoming free is the 512. Okay, so 512 cannot be placed in this remembered inode place, because in that case this 499 will be lost. Okay, so what you do is you simply mark inode number 512 on the disk as unallocated. Next time when this superblock free inode list becomes empty and you search for unallocated inodes, the search will start from 499 and eventually it will come to inode number 512. So that can be allocated. Whereas if the inode which is becoming free is the 100, okay, in that case what I do is I simply replace this 499 by 100, and by that I don't lose this 499, because 100 is less than 499 and my search will start from 100, so eventually I will come to inode number 499. Okay, so these are the techniques which will be used for inode allocation and freeing an inode. So effectively the algorithms will look like this. In the first case, when I have to allocate a new inode to a newly created directory or a newly created file, the algorithm will call as ialloc, that is allocation of a new inode. So the algorithm will be like this, while not done. So this will be the entire algorithm for allocation of an unallocated inode to a newly created file or a newly created directory. So first, if you find that the superblock is locked while trying to get an unallocated inode, then the process has to sleep until the superblock becomes free. If it is not locked, then within the superblock you have to check whether the superblock free inode list is empty or not. If the superblock free inode list is not empty, then I don't have any problem. I can simply get an inode number from the superblock free inode list, then get inode. Here what I have is I have an inode from the disk, but for working on this inode, I have to have an in-core copy. So for this inode number which has been acquired, I have to get an in-core copy where this inode can be copied. So for that I have an iget algorithm, that is get an in-core inode. Okay. Once you get that, then you have to initialize the inode. So for initialization, what I mean is you have to set the reference count equal to 1 and other necessary things. So once that is done, then this updated copy of the in-core inode has to be saved onto the disk inode. So you write the inode to disk. Okay. After that, because earlier there were a number of inodes which are free, from which one of the inodes have been allocated to this newly created process, is being allocated to the newly created process. So the file system free inode count has to be decremented by 1. Okay. This information is also maintained in the superblock. After that, this inode has to be given to the process. Okay. But in case the superblock free inode list is empty, as I said, when it becomes empty, then I have to get the remembered inode, copy the following free inodes, unallocated inodes, into the superblock free inode list. So that is what is done here. In case the superblock free inode list is empty, because you are copying the data from you are copying a list of unallocated inode numbers into the superblock, that means you are working on the superblock. So the superblock has to be locked before you perform this task. So you lock the superblock, get remembered inode number from the for free inode search, from the point from where search for unallocated inodes will become. Okay. So you search for the free inodes, and the superblock free inode list will be filled up until the superblock free inode list is full. So if it can contain 100 inode numbers, then maximum 100 I can put. I cannot put anything more than that. Or there may be situation that after getting 50 unallocated inodes, I find that there is no other unallocated inode on the file system. All the remaining inodes have been allocated. So if one of these conditions are satisfied, that until the superblock full or no more free inodes, then search operation has to stop. Okay. After that, you have to unlock the superblock. Now in this case, I had a number of processes which can sleep on the event that superblock becomes free. So all those processes have to wake up now once the superblock becomes unlocked. So you wake up all processes which were sleeping on the event that superblock becomes free. Then after that, you check that no free inode found on the disk. Superblock was empty, and I could not get any unallocated inode on the disk which can be copied into the superblock free inode list. So naturally, no other file or no other directory can be created. So we return with no inode. Okay. Then otherwise, if we get one or more inodes on the superblock, one or more inodes on the disk which are unallocated, then to facilitate the following search operation, search for search for free inode numbers, we have to set the remembered inode. Okay. So set the remembered inode, and by this time the superblock free inode list has got a number of unallocated inode numbers. Okay, and the following thing will continue, that you get inode number for superblock from the superblock inode list, and the rest of the things will be similar to if I get a free inode on the superblock free inode list. Okay, so this will be the algorithm which is followed for getting an unallocated inode for a newly created file or a newly created. Okay. So with this, stop today.